It's a great way to end start the recording. So welcome back, everybody. Hope everyone had a good weekend. As a reminder, so normally we were scheduled to have our exam today, but I have extended it. I have moved it back to Thursday. So we're gonna finish off 1.7. We're gonna do this this extra example here, and then we will move on to 2.1, which while it does not have while it is new material that will not be covered on exam one, it does have a few things that are review for that material. So please look. That is good news. As a reminder, there is an exam review posted on our course homepage along with the solution guide. As it says on the review itself, my recommendation has always been when it comes to reviews to study up, try the review with nothing else, just a pen, pencil, calculator. And then if you get if you get stumped, put a dash mark next to it or something and come back to it and then check your answers with the answer key that's at the end of the solution guide, at the end of the review document. And then if you get them right, kudos, that's excellent. If you get them wrong, try it again. Maybe study up before you try it again, and then try it again. Once again, without any help from anything else. Otherwise, you will develop a crutch. Um, and after that, if you still get it wrong, then look at the solution guide, but then try it again at a later date, maybe an hour later, a day later, whatever it may be, to see if you've truly gotten it into your long-term memory. So feel free to use that to help you aid in your study. But we've got this function here that I want to do as a good practice for piecewise functions. So it wants us to graph this function. This function has two dividing values. It has x equals -3 and x equals 0. And so the way we want to do this is first and foremost, we want to break it up by piece and use a color coding technique. So I'm going to label this as 1, this is 2, and this is 3. And once again, you don't even need to have color to do this. You can, and I'd be willing to even accept this on an exam if maybe you make this one a straight line, this one a dashed line, and this one a squiggly line like that. I'm okay with that. It won't look perfect, but I'm okay with it. The only reason why I suggest that is because this will make it a lot easier to determine which piece goes where and to make sure that you don't overextend a piece. So either way, piece one is defined for all x values strictly less than -3. So we'll find -3 at the very bottom, and it's all numbers less than but not equal to -3. So it's a parenthesis there, and that's piece one. Piece two is defined between -3 and 0, where it includes -3 but excludes 0. So it'll be a bracket at -3 and a parenthesis at 0. And that's piece two. And then piece three is for all values greater than or equal to 0. So that's going to be a bracket and onwards for piece three. This thing here is meant to make sure that I do, like, especially if I do color code it, which I am totally okay with. Yes, the pieces will look in different colors, but when you don't have to do this, but as you're starting out, it's always a good idea. So now that we've broken it down into pieces, now what we need to do is figure out where each piece starts and where each piece ends, because piece one ends at -3. Piece two starts at -3 and ends at 0, and piece three starts at 0 and goes on forever. So we need to find out where they start and where they end. So we'll use the dividing values to figure that out. We'll plug the dividing values into each function that it corresponds to, and then put the solid dot if it's like a solid closed dot if it's included, an open circle if it's excluded. The reason why we're doing it in both, once again, is so that we know where the pieces end and start. Even though it might not be a point on the actual curve, we need to know where it ends. So we'll do at x equals -3. That dividing value belongs to piece one and piece two. So we'll try it for 1. Y will just equal 1. when our x values are less than -3, when we're the first function, we're just the constant function 1. So when we try and plug in -3, there's no x's to plug it into, so it just becomes automatically 1. And so we have the point -3 comma +1, and it's going to be an open circle. We didn't get to plug it in, but we did. Like there was no place to plug it in, but we tried to plug it in. That's why when we plugged in x equals -3, we got a y value of 1. There was no x's to do, so it was vacuously satisfied. And because it is strict for piece 1, it is strictly less than 3. Its restriction right here says strictly less than -3. It's going to be an open circle. So we'll go ahead and jot that down. -3 comma +1 right there. And then we'll plug it into 2. So here, if we plugged in -3, piece 2 is defined as the function -x. So when we plug in -3, it becomes -3, which is +3. So we have the point -3 comma +3, and that's going to be a closed dot. So right there. Even though it isn't actually a point on the red curve on piece 1, we have to put it there so we know where to end. That's the idea. So those are the two functions that involve the dividing value at -3. Now we'll move on to the second dividing value, which is 0. At x equals 0, the two functions that are involved are piece 2 and piece 3. That's the dividing value that those two pieces share. So we'll plug it into each. Piece 2, if you plug in 0 into that, you're going to get y equals -0, which is just 0. So we have the point 0, 0. Will that be an open circle or a closed dot? Don't say it out loud so like everyone gets a chance to think as they're writing down. We plugged in 0 into piece 2 to find out where it ends. But because it is a strict inequality there, it is going to be an open circle. Strict means it's not existing there. Non-existence means an open circle. So we'll put an open circle there. Open circle. And then we'll plug it into the third function as well. So if I plug it into the third function, that's x squared. So plugging 0 into that is 0 squared, which equals 0. So I have the point 0, 0. And this one, because it is included, is going to be a solid dot or a closed dot. But look at that. It fills it in. And that's okay. So I'm going to zoom in so you can see that it fills in the blank. Does anybody have any questions about this stuff right here? This is the first step. Yes, Ben.
Why did you decide on using -3?
Those were the dividing values listed here. So that's my jargon. I don't think textbooks ever really describe what those numbers are, but I call them the dividing values because they are the values that divide up the pieces. So I'm choosing -3 because that's the value that they share. That's where piece 1 ends and piece 2 begins. And here's a cool thing. If this had instead been -3, if it had been -2, then this curve would have 3 dividing values. It would have -3 because that's where piece 1 ends, -2 and 0 because that's where piece 2 starts and ends. And then we already included 0 but 0 as well because that's where piece 3 starts. Cheyenne, yes.
Is that the reason that x equals 0, they're using piece 2 and piece 3 like together?
That's correct. We're using piece 2 and piece 3 on, so Cheyenne is absolutely correct. We're using only piece 2 and piece 3 for x equals 0 because that's the dividing value that these two functions share. Does anybody have any other questions? Those are great questions to ask. Yes.
Yeah, I'm still a little confused. So you plug in -3 for the x instead, right?
Mm-hmm.
That doesn't make the first piece true. -3 is not greater than -3 or less than -3.
So remember, oh, and I'm glad you mentioned this because this is a very, very common misconception. Once we've plugged in an X value, we get a Y value. And a Y value doesn't need to doesn't need to worry about an X restriction. Does that make sense?
Oh, okay, so the only thing, like the X is less than -3
Yes.
is only strict for the Y value.
It's only strict for the X value. Yes.
Okay,
So like the X values, they need to be less than 3, but the Y values could be whatever. Once you plug it in, you get a Y value, and Y values don't need to worry about these restrictions.
so we're plugging in a Y value for the X on the right?
No, we're plugging in an X value and getting a corresponding Y value. Is that
I think so.
okay?
That makes sense.
So when it comes to piecewise functions, the pieces are defined by particular values of X. And whatever number they produce when you plug in that X value, that number is just going to give you the coordinate point on the curve, on the graph. It has no bearing on the domain restrictions here because those are only in terms of X. So going back here for just a second, we did one over here. So when we plug in -1, we plug it into piece 1 because that is an X value. That is an X value that is less than 0. But we got a Y value of 2. That's a Y value. It doesn't need to satisfy this condition. Does that make sense?
Yeah.
Good, good. So, yes, Thomas.
How would you use the second one twice when getting X equals -3 and then X equals 0?
So we're the first time we're figuring out where piece 2 starts.
Yes.
And then the second time we plug in 0, we're trying to find out where it ends.
It's like 2 parts into the second.
Yes.
It's like -3, that's on X, and then we solve for that one, and then X equals 0, then we do the same thing.
Yes.
The other half.
Exactly. To find the other end point of it, the start and end of it.
Because Alex doesn't really explain that.
Yeah, no, it's like I have gone back and forth many a time. I love Alex for what it does, but there are a couple things where it does not do well. And honestly, it's just a limitation of the medium. No program. I've never met a program. I've never actually met a program in real life. It's impossible, but I have never seen a program, an online homework system that does piecewise functions justice. It always ends up being a mess. And so I've gone back and forth on whether or not I want to give you guys a written homework assignment for that material or just skip it and just just pay attention to my notes and that's it. I've gone back and forth and this is what I finally decided was to try and use Alex. They do the whole thing about continuity, which I disagree with, but either way. Any other questions?
So,
Yeah.
if it wasn't, -3 is less than or equal to X, less than 0, if the equal to wasn't there, would you plug in like -2 instead, or?
If it was like this, so are you let me
If the equal to wasn't there?
this equal to if that was gone? So excellent question. So if everyone's looking, I erased the or equal to here. Well, then it wouldn't exist in either piece 1 or piece 2. So instead of them one being a closed dot, this would now be an open circle. Because we need to know where the function stops. Oh, yeah, but or starts for blue, but it's still there. It's still an important placeholder, but it's no longer existing there. Neither function exists at -3. That's why we have to have both open circles because the function doesn't exist there. If we put a solid dot, then the function would exist at -3, but it doesn't. In this case. Is that okay?
Mhm.
So excellent question. So we would still plug in -3 because that's where the function ends or starts, yeah, for blue. All right. Any other questions? These are great questions about this stuff. Please keep them up. They're great at understanding all this nuance. My favorite thing in life, nuance. Nuance is the best. So now that we've found all the dividing value points, we can start working on filling in the rest of the graph. And so just as a small note, so once again, this point got filled in by the green. It was an open circle, but then the green curve kind of filled it in for us. So the function does exist there and does equal 0. Yes, Alita. It's all right.
Um, It does ask like, is this function continuous?
Yes.
Yeah, that's the part where I had like a hard time with.
So in essence, what that is, so don't worry about that for the exam. I'm not going to ask that question. I wish I could remove that part of the question, but they don't let me edit that part of it. What they're trying to do is talk to you about continuity, which is a calculus concept, which is why I don't really agree with it. In calculus, you'll talk about continuity. This orange graph that I've drawn is a continuous graph because you can draw it with one continuous pen mark. Whereas if I do this, that is not continuous because I had to lift my pen from the page and I couldn't continuously draw it. So if the curve is all connected into one thing, it is a continuous graph. If it's not, so for example, this one right here is not continuous. However, if it just so happened, wait, let me get that. If it just so happened that this filled in this spot right there, this would be continuous because you could draw it with one pen stroke. Does that make sense? So you won't have to worry about that for the exam because I don't agree with that. I don't think it's really necessary right now because in order to talk about continuity, you need to have a concept called limits, which is something that you will discuss in calculus in the beginning. If you remember Lindsay Lohan and Mean Girls, remember that scene where it's like the limit does not exist? That scene will make way more sense once you get into 181.
Because then Alex, there's also a part where you grab it, of course, and then you like make the line segment puncture through another line. That was really tricky because it's really picky in which one to do.
Yeah, it's a problem, but
It's continental English.
I'm sorry. Sometimes learning does do that though. So, last bit. Now that we found the dividing values, now we need to fill in the rest of the graph. And the way we do that is with our knowledge of functions. So, for piece one, the curve that piece one is defining is the curve y equals 1. That is a horizontal line. Y equals 1 is a flat line. And so for everything left of -3, it is the constant curve positive 1. So all we need to do is just draw a horizontal line like that. For piece 2, we have y equals -x, which is a line with slope -1. And it has a y-intercept of 0, which we can use, but because it's a line and we already have 2 points, we can just connect it immediately. Or you can use the slope, right? We know this, we've already got 2 points, and that's enough to draw a line. As long as you have 2 points, you can draw a line. But you can also go, okay, down 1, right 1, down 1, right 1, and you can find points that way to connect the graph. But since we already have these 2 points, that should be good enough. And that's the curve y equals -x. That's the line y equals -x, just for that little segment though. And then piece 3. So for piece 3, you have y equals x squared. That is x to the even. So it has the points 0, 0, 1, 1, and makes the U shape. Right? From the library of functions, all the x to the evens make the U shapes. X squared, x to the 4th, x to the 16th, x to the 200th. The only difference is that the higher the degree, the higher the power, it becomes more jagged. But since this is the second degree, this is degree 2, it's not going to be very jagged at all. It's just going to be a nice smooth curve. We know it has the point 1, 1. X squared, ignoring the piecewise function for just a moment, the curve y equals x squared also does have -1 comma, oh, that's not -1, 1. That's -1, 1. I'm sorry. It technically also has this point right here on the left, but the curve is only defined for numbers greater than or equal to 0. So we don't plot that point because that would be a point belonging to the blue graph. Does that make sense? One more time, just to reiterate. Yes, the U shape always has the points -1, +1, 0, 0, and 1, 1, but we're not going to worry about that one because that belongs to the blue graph. That belongs to the blue graph. So we only have to do the right half of the U shape. So it looks like that. And that's our curve. And this is by the Alex problems, this would be not continuous. If this piece right here had been shifted up, then it would be continuous. That would make it continuous, but it's not because you cannot draw it with one continuous line. Yes.
Probably a silly question, but how do you use the scissors on Alex? Because I tried to use it to make like draw a curve on there,
Uh-huh.
but only half of it.
The scissors.
And there was like a little scissors button that you could use to cut it.
Ooh, that's new.
What you gotta do is you gotta put in the point that you're like trying to cut up from and then get the eraser and you just cut them.
Oh, cut that point above it,
You
okay,
cut where you wanna.
okay, I thought it was like, just cut it
Yeah.
there, okay, cool, thank you.
Fascinating. That's new. That's awesome. They didn't have that last semester, so at least not to my knowledge. So that's cool that they've got a snipping feature now. Sorry, I'll have to look at that more in detail. They don't alert me when they make small changes like that, but I'll look into that. I'm gonna make a comment to myself. Snippet feature. Thank you. I just want to make sure I mention that to myself. Okay. Any other questions on that one? So the key thing, dividing it up, finding where each piece starts and where each piece ends by using the dividing values, and then using your knowledge of functions, usually lines. Like I can promise you, if there is going to be one of these on the exam, it will only deal with lines. You don't need to worry about parabolas and stuff when that happens. That's going to be for later on, because we don't have too much knowledge of how to work with parabolas yet. That's going to be in the next section in just a moment. Any questions on that? Okay. Then we will start up Unit 2. So Unit 2 is all about polynomials, and then rational functions, but we'll get there. We'll get there in just a little bit. But it's all about polynomials. And so this is new material. This is not covered on exam 1. But there is a little bit of a reminder here about completing the square. So if we're going to learn about polynomials, and we've already learned about degree 1 polynomials, we've already learned about lines. Lines are degree 1 polynomials. So the next natural choice to start studying are quadratic functions. And the reason we do that is that a lot of life can be modeled by quadratic functions. If you've ever thrown a ball up into the air, that's a quadratic function. The measurement of how high it goes up and like hits its apex and then starts falling down, that's a quadratic function. That's a parabola. There are many opportunities to use parabolas in certain areas, usually very contrived, yes.
And what that math ties into science of gravity and physics. Right?
Yes. Gravity is affecting, and like that's partly why it works. Why the shape ends up arcing the way it does is because of gravity.
And that's the math.
Yes, that's the math behind it.
Okay.
Now, if you've ever you'll occasionally see a word problem in this section, and it will be very contrived. I understand there's never going to be these real life situations like this, but you can see how it could be used, especially with computer programming and stuff to try and optimize everything. And so the other reason why, from a mathematical perspective, is it's interesting that degree 2 has a lot of information. Degree 3 and beyond, they start to lose out on unique properties. Quadratic functions have some very nice, neat properties. So in order to get started, we do need to relearn a little bit or review our completing the square. This is helpful for a lot of reasons because this will come up again and again, as I've said. We're going to do it here a couple times. In Math 127, you'll do it when you start studying hyperbolas and ellipses. You'll start doing it in calculus specifically. I mean, you might do it in calculus 1 a little bit, but it really becomes apparent in calc 2 when you talk about what we call trigonometric integrals. So this does show its head quite frequently in mathematics. The key steps are that completing the square is very, very nice if you have a leading coefficient of 1. But if you don't have a leading coefficient of 1, you should factor it out from the first two terms. You don't need to worry about the third term. It's not going to be very, very relevant for completing the square. So we're going to factor out that. So in our example, we're going to factor out the -3 from the first and second terms. And factoring out a negative will change the sign of everything involved. So instead of having a -3x squared, it's now a positive x squared. Instead of a plus 24x, it's now going to become a minus 8x. And then don't forget about your minus 19 on the outside. It's very, very rare that like we try to make it nice and neat for you guys. Maybe we shouldn't. Maybe we should make it not as nice numbers because we've got calculators. But the fact of the matter is the 19, it's very rare that the C term ever is divisible by the A value. So just ignore it for now. And then the whole point of that is that on the inside of the parentheses, now we have a leading coefficient of 1. So we can use our method, which is to find half the B term, square it, and then add and subtract it. So half the B term, I'm gonna rewrite it. So -3 times x squared minus 8x minus 19. The B term is -8, which means that B over 2 squared is -4 quantity squared, which is positive 16. Half the B value is -8, half that is -4. Squaring that gives you 16. So on the inside of the parentheses, I'm going to do my little trick of cleverly adding 0. Very, very important mathematical trick. And this becomes -3 times x squared minus 8x plus 16 minus 16 to cleverly add 0. Because once again, we can cleverly add 0 because adding 0 doesn't change anything. That's why I can still say these two things are equal. If I just add 16, that fundamentally changes the expression. But if I add 16 and then immediately subtract it, that does nothing to the actual, it remains balanced. But the whole point is that these three terms now, they make a perfect square trinomial. They make x minus 4 quantity squared. And it's always, as a reminder, you might remember this, but if not, you don't even need to try and factor this yourself to figure it out. By design, and we talked about this in 1.2, so if you want to go back and review why it's true, we did kind of briefly talk about why this works, but this value right here will always be b over 2. So b over 2 is -4, right there. If this was positive 10x right here, then this would become x plus 5. Because half 10 is 5. Half of positive 10 is 5. So anyways, then the last step is to simplify via distribution to finalize the expression. So we have -3 times bracket, parenthesis, x minus 4 quantity squared minus 16 minus 19. But that's not exactly the way we want it. So we want to distribute the -3 in front, to both terms of the inside of the brackets. And we end up with -3 times the quantity x minus 4 squared plus 48 minus 19. Because when I distribute the -3 into the -16, I get positive 48. And then we'll combine the positive 48 and the minus 19 to get our final answer, which is -3 times x minus 4 squared plus 29. Yes. And that is the completed square. That's the distribution of the -3 into the -16.
Oh, okay.
Mm-hmm. So we're going to need to use that because now it's time to actually talk about quadratic functions. Or so we can say either quadratic or we can say parabolic functions. So there are two different forms of it, just like there were two different forms of circles. There is standard form, which is y equals ax squared plus bx plus c. That is standard form. Standard form or general form is always going to be it in simplest format where all the terms are expanded. But there's also a thing called vertex form. And vertex form is y equals a times the quantity x minus h squared plus k, where h comma k is equal to the vertex. So if you want to go from standard form to vertex form, you need to complete the square. But if you want to go from vertex form to standard form, you've got to simplify. Completing the square is how you go from standard form to vertex form, simplifying it. So boiling out the x minus h squared, so leaving x minus h times x minus h, distributing in the a, combining like terms, that's how you get into standard form. But a key note about that, this is the exact same a. H and K are not B and C. They're not. But A is the exact same. That'll be an important information. That'll be a very useful fact for parabolic functions. And why do we need to know both formats? Well, they have different uses. And the good news is, if you don't like dealing with vertex form, there are ways to avoid it, as we'll learn. But it's never bad to know both of them. But we'll learn in a little bit how to get by with just standard form. So here's the thing. So looking at the picture, all parabolic functions either look like that or a negative version of their counterpart. And how that gets determined is just is something in a moment. So right here we have the x value h, and down here we have a y value of k. And so this point right here with the coordinate point h comma k, that is the vertex. The vertex is always found from vertex form. It's h comma k. It's where the curve goes from going down to up or from up to down, depending on whether it's opening upwards or downwards. And then we also have one other thing that's useful, which is what we call the axis of symmetry, which is a line that cuts right straight through the h value of your vertex, the x coordinate of your vertex. This is called the axis of symmetry, or AOS, and it's x equals h. I'm going to abbreviate it as AOS from now on because I don't want to write axis symmetry. But it's a vertical line, and all vertical lines, as we remember from 1.4/5, is that all vertical lines are of the form x equals a number, where the number in question is the x coordinate of any point that it goes through. So since this goes through the point h comma k, it's going to be x equals h. And the reason why the axis of symmetry is very, very nice is that it means that all the points to the left and to the right, they're equidistant. So if I have this point right here, then there is a mirror image point right over, and I'm going to draw a little line right over here, and this distance is the exact same. you guys remember the two hash marks to mean equal, like equal length? If you don't, when you write two tick marks or one tick mark or three tick marks, any segment that has the same number of tick marks means it's the same length. And so that's going to be useful in a little bit when it comes to graphing these guys or girls or them, whatever you want to do. So that is that. Now, the reason why I wanted to draw your attention to the A value is it's very, very important. It does something that none of the other constants do. It tells you whether or not the parabola opens upward or downward. If A is greater than 0, then the parabola opens upward. Now, we won't get into too much of this, like this context. We won't get into too much of it, but just so you have the terminology, this is concave up. And so you can memorize this fact if you really want to, or you can memorize this first fact and then deduce what the last point is. If it's upward, and so the way I've memorized it is if your A value is positive, right? It's greater than 0, meaning it's positive. If you're feeling positive, you got to smile. And so that's an upward shape like this, right? We can have a little guy right here. And he's got a little tongue sticking out. He's a happy face, right? There you go. So if you've got an upward facing, then your vertex is at the very bottom of your graph, because that's going to be the lowest point. So when your A value is positive, you're opening upward, which means that your vertex is a relative minimum. In stark contrast, if your A value is less than 0, then the graph of the parabola opens downward. And so the parabola is what we call concave down. And if you've got it and the way I remember this one is if your A value is less than 0, that means your A value is negative. And if you ever see a negative person, they're not happy. They've got a frown. So they look like this. They're not happy, right? So, but if you were to draw that curve, the vertex is at the very top. So the vertex is a relative maximum. So even without knowing where the vertex is or anything else, as long as you see the A value, you automatically know whether or not it has a relative maximum or a relative minimum. So we're going to see how we can get through any of this information. We can get all of this information just by looking at the function. Determine where the graph, whether the graph opens upward or downward, where its vertex is and its axis of symmetry, and finally determine if it has a relative max or a relative min. So I don't expect you to have vertex form memorized. So as a reminder, vertex form is y equals a times x minus h squared plus k. So part A is in vertex form, though it doesn't look perfect yet. So what's the A value? 1. Yes, there's an implied, because mathematicians are lazy, there's an implied 1 here. So A is equal to 1, which means that it's positive, which means that the graph will open upwards. The A value is 1, that's a positive number, so the graph opens upwards. Now, we don't even, and so we can actually just immediately use this to figure out whether or not the curve has a relative maximum or relative minimum. To be clear, I don't have this memorized. I have that first fact memorized. If A is greater than 0, then it's upward, and then I deduce the other one. If I remember the first one, if I remember that if A is greater than 0, then it opens upward, then the other option has to be downward. If A is less than 0, it's downward. And then I use that information with my knowledge of what the graph would look like to figure this out. I don't have it memorized. I mean, I never had it memorized. In fact, the only reason I have it memorized now is because I've taught it for so many years. But if it opens upward, you've got a smiley face, which means your vertex is at the very bottom, meaning that it's a relative minimum. So we can take this information to figure out what this should be, and that is, this is a relative minimum. So with the A value, you already know a lot about the shape. The only thing left to do is find the vertex and the axis of symmetry. If you find the vertex, you automatically have the axis of symmetry, which we'll see in a second. So I'm going to tell you that the vertex is -5, -62. And I want you to think about why. Take a second, try and convince yourself of why that would be true. Just keeping it quiet for a second. Yes, totally fine. I'm with you though. I'm with you. That was me. That was me 100% of my classes. I was that guy. I was that guy.
And it's already, as you move into the left, since it's positive, then it's already going to x equals -5.
Yes.
Then that's already the axis of symmetry.
So yes, you can, that's a good point. You can use your knowledge of transformations of functions to do this, or you can try and fit it into the format just like you did with circles. The fact of the matter is it's x minus h. So instead, what we would want to write this as is 1 times x minus -5 squared plus -62. That's how it fits into it. Now that's what we're seeing this first time. Normally, we're going to skip doing this and do this in our head. So we're double negating it so that it fits into that x minus h format and plus k. But in practice, so in short, the x value gets opposite signs and the y value keeps its sign. That's in practice, but I'd rather you understand that you have to fit it into this format. So that's the axis of the vertex, and the axis of symmetry is the x value of your vertex. There's no other way to get it. Your axis of symmetry has to go through your vertex. So from here, from this -5, we automatically know that the axis of symmetry is x equals -5. Now, I don't recall off the top of my head, but I'm pretty sure Alex makes you write it as x equals. If they don't, that's a disservice because you don't, do they?
Yeah, they'll say, you didn't, they'll count you wrong, but they'll make sure before you, like cement, they say, make you write it as an equation.
Yes, because an axis of symmetry is a line. It is an equation. So it should, like, saying the axis of symmetry is -5 is not actually anything mathematically valid because you're talking about an equation, not a number. And so I hate to do that, but it's like, it's kind of a technicality. It's the mathematical equivalent of like forgetting to capitalize your first letter of a sentence, right? Even if you have the best argument ever in your thesis of your English document, if you don't capitalize the first letter of your sentences, they're going to mark you down like a point. Yes, Ben.
Is there ever a time where that is gonna be over y?
Nope. It'll always be the x value because that's what it cuts through. And since it's a vertical line, it's always going to be x equals. And it's going to be x equals in particular the numbers, the x coordinate that it goes through. Every single point on this line always has an x value of h. So, good. Any other questions? Great questions. This next one, f of x equals -1/2 x squared plus 1. Now, this is an interesting case because this curve, this one right here, is both in vertex form and in general form. That happens on occasion. But this is actually, technically speaking, in vertex form because what I can do is I can rewrite it as -1/2 times x minus 0 squared plus 1. So it is already in vertex form. The only reason I can do this is because there's no x term. There's no x to the first power term. If there was an x to the first power term, I need to complete the square. So, does this graph open upwards or downwards?
Down.
Down. Why? the negative 1/2. The A value is negative 1/2. A is equal to negative 1/2. That's less than 0, so the graph opens downward. And because of that information, we can immediately figure out whether or not it has a relative max or a relative min. If it opens down, you got a frown, and that means that your vertex will be located at the top of your graph, so it's going to be a relative maximum. The other reason why I like this even though there isn't much application in real life, other than if you see me at a Target or whatever, or a Magic the Gathering store, not that I'd ever go to one, but if I did, if I went to a card shop, then you might see me there and I'd bust out this question. But what I love about this material is that this is a really good example of how you can let your brain deduce mathematics. Instead of having to try and memorize 80 million different facts, just memorize this one fact, that if A is less than 0, it opens downward, and then everything else pretty much comes naturally, which I like. So the vertex is 0, positive 1. And because it goes, the vertex has an x coordinate of 0, and your axis of symmetry goes straight through your vertex, it means that your axis of symmetry is x equals 0. Any questions on that? Okay. Now, one of my students in my other class noticed right away that this one, if you factor out the 2, it's a perfect square trinomial. So you can already, you don't need to worry about completing the square at all because it's already done for us. That being said, this student was very, very clever at this one. I don't expect us to be clever. That's not what I designed my class for. I don't want, I'd like you to become clever, but that's not something that happens naturally. And it definitely doesn't happen on an exam. When we're taking an exam, we're not trying to think about how cleverly we can concisely write it. We're just trying to solve the problem. So the good news is, though, you don't have to know that it's a perfect square, perfect square trinomial to figure this one out. What we're going to do instead is we're going to get this into vertex form, because as it stands right now, there is no way to find out the vertex unless we're in vertex form. There will be a way soon. So we're going to need in vertex form, which means we need to complete the square. I'll get this started for you, but I want you to finish it. When you're completing the square, if you don't have a leading coefficient of 1, which we don't in this case, you factor out the A term from the first two, you factor out the A value, the A coefficient from the first 2 terms. So this is Q of X equals 2 times parentheses, X squared minus 14X, and then plus your 98 over here. Go ahead and complete the square on the inside of the parentheses. I'll slowly fill in details. I'm going to pause the recording so that people are just waiting. All right, so I've resumed the recording. This is what you should get when you complete the square. You should get Q of X is equal to 2 times X minus 7 squared. And so one thing we were talking about, we had just a few questions while we had the recording paused. Just as a little fun tidbit for all of us, I can promise you there will always be at least one graphing question. Whether it's making a graph or interpreting a graph, that's up for debate. Usually I have at least one interpreting a graph problem on every exam because that's my favorite thing to do. I love interpreting graph problems. So you can always expect to see at least one of those. So that's giving you a little bit of a heads up on the exam. Yes. So why is it minus 98 plus 98? So when we complete the square, we add 49, then we subtract 49. We add half the b term squared. And then the reason why is the first 3 terms will then make a perfect square trinomial, but you still have that minus 48 on the inside of these parentheses. So we have to distribute the 2, and that's where I get the minus 98, because 2 times negative 49 is minus 98, but we still have that plus 98, and then those end up canceling. So Our A value is, we haven't used, no, we've used almost all the colors. Well, let's use brown. Our A value is 2, which is positive. So this graph opens upward. If your A value is positive, you're feeling positive and you've got a smile, meaning it opens upward. And if it opens upward, then your function has a relative min because the vertex would be at the bottom of your smile. Now the vertex, oh no. What's the vertex?
Vertex is,
7 for the x coordinate. What's the y coordinate? 0, yes. There's an implied +0 here. So the vertex is 7, 0, because it already fits into the right format of x minus h. It already fits into that x minus h category because it's -7. And then the axis of symmetry has to come from the x coordinate, so it's x equals 7. Any questions on that? Because it didn't have a plus k, so we just rewrite it as +0
Okay.
to find what the k
If
value
there
is.
is a K, then that would be.
Yeah, if it had been x, if this had been +1, then it would be 1 here. But it didn't have anything, so it's 0. All right, any questions on that?
on that second part, you're distributing the 2 into the -49 and the +49, or just the negative?
Just the -49 because so I usually write this in 2 steps, but I didn't this time. Let me add that step if you
Get the -7x² from the first part, the purple part,
yes.
distribute the 2 into the -49.
Yes, so this all becomes x minus 7 squared. Is that okay?
Yeah.
Yeah, great question. All right, I think that makes it the perfect time to take our first break because I like to take them about every hour or so. So let's come back at 10:37. People watching the recording, go stretch, do some push-ups, something like that, and come back. All right, we're back and we'll continue onwards. So now we're going to talk about graphing them. So I need to make an edit to this one. The step 2 is going to be plot 2 more points. Plot 2 points. So when it comes to graphing them, the first thing you can do is if it's already in vertex form, which what this one is, you can immediately find at least 1 point on the graph. And you can also draw the axis of symmetry. So the vertex is at -4, -6. And that means that the AOS, the axis of symmetry, is x equals -4. We'll go ahead and plot those points, that point in that vertical line. Though I don't think Alex makes you draw the axis of symmetry, which is weird, even though they talk a lot about it. I make you draw it for a good reason, and I'll explain in just a moment. So -4, -6 is right there. And then we can draw a axis of symmetry through it. And you can label it if you want as x equals -4, but it's not necessary to do that as long as it's there. Now, the way Alex wants this done is they want you to plot 5 points. We already have 1, so that means we only need 4 more. However, I would argue that you only need 2 more because of the axis of symmetry. So next, plot 2 points by plugging in x values to the right or to the left. Always choose on the right or choose on the left. So for us, let's just do. You can pick whatever you want on the right or the left, but I would recommend trying to stay close to your vertex's x value, because these things are quadratics. They grow quite quickly. And so moving more than 2 spaces out starts getting very, very large numbers. So I'm going to do y of -3 which would be 2 times -3 plus 4 quantity squared minus 6. That would be -4. So we have the point -3 comma -4. So we can plot that point. -3 comma -4. And on an exam, on your homework, you don't need to write this information. You can just write y of -3 equals -4. You can use your calculator. It's just so we see where I plugged it in. And then I'll also do y of -2, another point on the right. And so that would be 2. I'm going to skip doing that. I'm just going to write it down. It'll be 2 times 2 squared, which is 4. So 8 minus 2, that's 2. So we have the point -2 comma +2. And we'll plot that point right there. Any questions on that?
Do you have to do 2?
So for me, 3 points is enough. You can do 1 point, plug in 1 point, like find the vertex, plot that point, find another point, like I did with y equals -3, and then what we're going to do here is use axis of symmetry to find the next point. So I'm okay with you just finding 3. That's my request. I'm fine with 3, but Alex, for whatever reason, wants 5. I'm not sure why. It has to do something with how the program works. Yes.
So I'm kind of confused, just like how I understand that you plug the numbers in on 2 with the parentheses -3 plus 4.
Mm-hmm.
And then I don't understand why it's not,
It's okay.
why you don't multiply like the 2 into there.
So the 2 is being, so what it's going to be is it's going to be +1 squared, which is just 1. So 2 times 1 is 2, minus 6 is 4, -4. That's where that's coming from.
Okay, I just.
Yeah, if the bracket was around it, then you'd multiply the 6 by 2 as well. Yeah. So then step 3 is, now that we have those 2 extra points, we can find 2 free points by using the axis of symmetry. What I mean by that is, because there is this point right here with a y value of -4 that is 1 unit away from the axis of symmetry, there is a directly equal point over here at -5 comma -4 by requirement. There is this kind of necessity of that this distance and this distance need to be the same. And the same thing is true with this point. So this point is 2 units away from the axis of symmetry. So there's going to be a point 2 units away on the other side at -6 comma 2. And that gives us 5 points. And so like what I drew here, I don't know if you can see the dot, yeah, you can see the dotted line a little bit. That's the same distance. So you can use your axis symmetry. That being said, there's nothing stopping you from just using your calculator and plugging it in. Your calculator has a save feature, so you can just use it and then plot more points. That's fine too. But you're going to need to plot points on the left and the right of the vertex in order for it to work. But now that you've got that, you have everything you need. You can graph it as such. And it does not need to be perfect. Alex will make it perfect for you, but that's how we do it with our caveman hands. Indeed. All right. Any questions on that? Yes. Oh, sure. So now let's do it again. This one, as a reminder, where's its vertex? +2, 0. So there's an implied +0 here. So the vertex is 2, 0, And that means that its AOS, its axis of symmetry, is x equals 2, always through the x coordinate. So a vertical line, so it's x equals, and it's an x coordinate, it's x equals the number of the x coordinate that it goes through. So let's go ahead and plot those. 2 comma 0 is right there, and we can draw a vertical line through 2 comma 0. And you can label your axis of symmetry, but it's fine to just leave it as is. I just like making my graphs look pretty, so I label it. And then all we need to do is plot points. Now here's the problem. This one has -3/4. That's a fraction. So if you plug in, let's do f of 3. I'm going to plot points to the right of it, but you could choose your points on the left of it as well. Whichever you choose is fine. If I do that, I'm going to get -3/4 times 3 minus 2 squared, which will be -3/4. So I have a point 3 comma -3/4. Now my graph is in half tick marks. I mean, like every grid line is on a 1 tick mark, but in between each one, I also have half tick marks, but I don't have quarter tick marks. So plotting that is very, very difficult on Alex. So you're gonna need to use that button that looks like this to plot the point. You're definitely gonna need to use that button to plot those points. Okay? If it ends up having a fraction, hopefully they don't. They usually don't, but if they do, not a big problem. Just plot them with the graphing point feature. So that's 1 point. We can plot that, and we'll also do f of 4. And this one we're going to luck out on because this is actually going to make, we're going to get 2 squared, which will be 4, and so it'll cancel out the fraction. But either way, so -3/4 times 4 minus 2 squared, that's going to be -3. So you have the point 4 comma -3. Let's plot those 2 points. 3 comma -3/4. That's right about there. And then 4 comma -3 is right about there. And then we can use the axis of symmetry to find 2 additional points. They have to be equidistant on the other side. So there should be a point right here and a point right there. 1 unit away, the same y value, 2 units away with the same y value. And then we complete the graph by connecting all the dots. And there we have it. Any questions on that? -3. So it'll be 2 squared, which is 4, and that'll cancel out the 1/4. Sorry, cancel the denominator of 4. So this will be -3/4 times 2 squared, which is 4, and then the 4's cancel. And all we're left with is a -3.
So square.
+4. That was the 3/4 from the beginning. So that cancels. Yes, that was me computing 2 squared. That's what this is.
Well, 2 squared again is 4.
Yes, so this is 2 squared, which is 4. So those cancel. All right. Oh,
So this is exactly similar to what we did last week in Alex, where it was like. You did like X and Y on one side, and then it was add to the left, and then add to the right, and then you just did 4. The exact same thing, just plus or minus 2.
yeah. Yeah. It's the cool thing about this is, and that brings up a good point, is with all of these ones, these are linear transformations of x squared, the U shape. So you don't even need to know this, this material. You can just use 1.6 to do this. But this is the way we can do it without having to deal with linear transformations if you don't want to. Now this last one, problem is it's not in vertex form. So we need to get it in vertex form. I'd like you guys to go ahead and do that. I'm going to pause the recording so I can do that as well. I'll change my mind. Instead of just completing the square, I want you to finish the whole problem. So to complete the square, we need to get b, our b value is 10. Our leading coefficient is already 1, so there's no need to factor any a values. So half the b term would be 5. Quantity squared is 25, so we add, subtract 25, which gives us perfect square trinomial, x plus 5 squared, and then negative 25 plus 29 is plus 4. That gives it vertex form, so we're able to find the vertex. It's negative 5 comma positive 4 because it has to fit into that x minus h formula. So we've got the vertex, and the axis of symmetry automatically comes from the x value of your vertex. So x equals negative 5, and we plotted that point and that vertical axis of symmetry. The reason I've drawn the axis of symmetry is to help me find the corresponding extra points. We were talking about during the pausing, though, that you can always just use your calculator to find 5 points. That is not illegal to do. So you can do it that way. I plugged in negative 4 and negative 3. I just choose one side of the x-axis, and then I can use the other two. I could have just as easily chose g of negative 6 and g of negative 7 to plot these 2 points and then find the purple points by axis of symmetry. It just happens that I like to choose the numbers on the right. Well, there's nothing wrong with choosing the numbers on the left. And then I have everything I need, and I can move on unless there's any questions. Any other questions? Okay. Now this one, what I like about this problem is that all the stuff below it, I don't even need the graph to figure it out. And actually, that's what we're going to do. I'm going to do it in reverse order, the way it's suggested. So first and foremost, though, there is a thing. I think we talked about it, but if we didn't, there was a thing called the square root property. Did we learn about this? I don't think we did. If we did, awesome. If we didn't, what it says is that if box squared equals a number, then the box equals plus or minus the square root of the number. The way it's usually worded is that if x squared equals k, then x equals plus or minus the square root of k. But it can be anything. It doesn't have to be x squared. It can be x minus 5 squared, or even x plus 2 squared, as we'll see in this problem. But we're going to kind of color code this. The parabola opens blank up or down. Well, the thing is, this thing is already in vertex form, so that's good. But our a value is negative 2, which is less than 0. So this opens up or down? Down. Opens downward. You can write down instead of downward if you want. And that means that the function has a relative max or min? Maximum. Because it's going to be a frown and the vertex will be at the top. Now, because it's already in vertex form, we can find the vertex. The vertex that's being hidden is going to be negative 2 comma 8. Yeah. No worries. So we have the vertex, negative 2 comma positive 8. And that means automatically that the axis of symmetry is x equals negative 2. The x-intercepts. So x-intercepts and y-intercepts. This is good practice for the exam because we need to remember how to find them. The x-intercept, any intercept, you set the opposite variable equal to 0 because that's the opposite variable will be 0 at an x-intercept or a y-intercept. So for the x-intercepts, you're going to set y equal to 0, and you get 0 equals -2 times x plus 2 squared plus 8. Now, there's no harm in foiling this out, distributing like doing the x plus 2 times x plus 2, simplifying, and then factoring or using the quadratic formula. There's nothing wrong with that, but because it's already in vertex form, we can actually use the square root property, which is what I'm going to do here. So I'm going to bring the 2 times x plus 2 quantity squared to the other side by adding it to both sides to get 2 times x plus 2 squared equals 8. I'll divide both sides by 2. To get x plus 2 squared is equal to 4. And then I can take the square root of both sides. But please remember that if you take the square root of both sides of an equation, you have to have the plus or minus. The whole point of that is that will cancel the square and the square root. And I get that x plus 2 equals plus or minus 2. Yes.
So because you have the -2, then can't you just do the slope? Move down and over?
That only works for lines. Slope only works for lines, and this is quadratic. I wish it were not the case, but since it's a quadratic and not a line, you can't use slope. Oh, you didn't have a question. Oh. Any other ones? Oh, Alita.
How, when you are changing over the -2x plus 2 squared, it doesn't turn the parentheses into -2.
Because it's all one collection. And the only thing we're taking that whole collection and adding that whole collection to both sides. So what I'm doing here is I'm adding 2 times x plus 2 squared to both sides. Because that's going to cancel this. If I put a minus here, then it's not the same thing and it won't cancel. Does that make sense? Yeah.
So instead of making the -8, instead of doing a -8, you're doing just getting rid of the negative.
Yes, you could, but you could just as easily. So, as Connor's suggesting, what you could do instead, and it would do the exact same thing as you could subtract 8 and get this, but you'll get the exact same thing. Yeah, Jade.
Yeah, so without going as far to do the square root property, can't you just assume that x-intercepts would be -2 and 2, just because the axis of symmetry says x equals negative, so you can assume.
So yes, you could find one of them, but you still need to find one before you can find the other. Yes, but that is a good point. If you know the axis of symmetry and you can find one of the x-intercepts, you automatically have the other one. Yeah. So this becomes x equals -2 plus or minus 2, which gives us two different answers. -2 plus 2 is 0, and -2 minus 2 is -4. So we have the x-intercepts 0, 0, and -4, 0. Now, you might be able to, if you notice this right away, you can find the y-intercept without doing any work. Because you have 0, 0, you automatically know where the other y-intercept is. It's you automatically know what the y-intercept is because it's 0, 0 as well. But that being said, let's just practice doing that. So the y-intercept is going to be setting x equal to 0. So we get y equals -2 times 0 plus 2 squared plus 8, which equals 0. Oh, and because of the vertex, we skipped a step here. We were able to figure out that it was a relative maximum, but now we know what the maximum value is and where it occurs. But we took a little detour to find the x and y intercepts. So let's continue down. We'll get to the function's relative maximum in just a moment. So the domain. Oh, go ahead, Ben.
Why is y-intercept not 8?
Excellent question. So the 8 gives us the vertex. The 8 is for the vertex. The vertex doesn't necessarily happen on the x-axis or the y-axis. So if it did, then it would be the y-intercept. But this one is not at 0, 8, so it's not going to be here. The vertex is over here.
Right? It's not just the 8 left over.
So excellent question. Excellent point. So when we do this, when we plug in 0, it's not 0 squared. It's 0 plus 2 squared. So that makes it 4 times -2 is -8, which cancels out the 8. That's why it's 0.
Gotcha.
Okay. Any other questions? All right. So the domain is a very, very quick one. It's honestly a formality, and I really dislike that they put it on these questions. But what are you going to do? Every once in a while, we have to jump through hoops. Even at work, you have to do the stupid things that you don't want to do. The domain, it's always going to be the answer is -infinity to +infinity. And the justification for that is, remember, this is a polynomial. Polynomials are defined everywhere. The only things we're looking out for when we're trying to find domains and ranges, specifically domains, is you want to make sure that it can plug into the function. So you need to make sure you're not dividing by 0 and you're not taking even roots of negative numbers. But that's never going to happen with a polynomial because polynomials are very nice. So that's why the domain and range of the domain of any quadratic is always -infinity to +infinity. Now the range, if you remember from way back when, in 1.3, I told you guys that finding the domain algebraically is something we can do, but finding the range algebraically is a much taller order. There are a few circumstances where you can do it algebraically, and this is one of them. So we know that this parabola is going to open downwards, right? So it's going to look something like this. Whatever it may be, that's not actually what it is. But that means that its range is going to go from -infinity, because we start our ranges by looking at the bottoms first and then working our way up. And where's it going to stop? There's a specific name for the point at which it's going to stop. At the vertex. So we know what the vertex is. It's -2, 8. So the largest y value that gets attained is 8. So we can automatically assume that the range is -infinity to +8 with a bracket on it. And so we can write that little bit of information. Since opens downward, the vertex has the largest y value attainable by the graph. So the range you can do without graphing it. It's not hard. It's not the end of the world to graph it first, but I just want to show you that you can do it without that information. You can automatically find it just by knowing where the vertex is and using your knowledge of the downward shape to figure it out. But either way. So the vertex will be the relative maximum. And as such, we know what the relative maximum value is and where it occurs. The value is always the y coordinate, and then the x value is the x value. So it has a relative maximum value of 8, and it occurs at -2. So with all of that information, unless there's any questions on any of that, largest since it opens downward, the vertex has the largest y value attainable. That's a the. You guys can tell that's a the, right? That's clearly a the, right? Let me erase my shame. The context.
Vacuously satisfied.
Clear from the context and vacuously satisfied are the two things that I hate when mathematicians say.
very protected.
It does sound very pretentious. And then also, my thing is, I mean, that's even what my thesis was about. I really dislike it because I like to learn on my own sometimes. I like to self-learn on textbooks. And so if it says clear from the context and I don't see it, then I can't figure out what it is unless I were to have a professor to answer it for, but I don't. So my whole thesis was trying to make sure a concept that was very, very complicated in complex analysis was understandable. So that's what mine was, is just breaking it down into pieces so that would be understandable. Okay. All right. So now the question that you might have is, do I have to always do convert from standard form to vertex form in order to find things out? Do I always have to complete the square? And the answer is luckily no. But you will have to memorize a formula. But it's not as hard as you think. So the vertex of any quadratic function in standard form, so f of x equals ax squared plus bx plus c, is located at x equals negative b over 2a. It always is. It's x equals negative b over 2a. Yes.
I was gonna ask the A part of it. Right.
Yes, it's part. So let me write that a little bit more clear. It's negative b over 2a. So to find the x value, compute negative b over 2a. That's going to be your x value. To find the y value. So remember, for any function, if you want to find a corresponding y value, you just plug the x value into the function. So to find the y value, plug x equals negative b over 2a into f. That is, find f of negative b over 2a. I write this differently than the way the book does it, but the vertex formula is that the vertex is located at the point negative b over 2a, comma, f of negative b over 2a. That's the function value, the y value. So you might think that this is memorizing a new formula, but it's not. It's just a part of a formula that we might already know. Does this look familiar at all? Does negative b over 2a look familiar? What does it look like? The quadratic formula. And there's a reason why. So check it out. The quadratic formula, right, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That gives you the zeros. That gives you the x-intercepts, right? And in particular, if you want to write this a little differently, it's negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. You could split it up. So the zeros happen where you take this value, negative b over 2a, and one of them is to the right of that by adding b squared minus 4ac over 2a, and the other one is on the left of it by subtracting. So when you're graphing a curve, when you're graphing a parabola, you have this 0, and then you have this 0. The value in the middle is negative b over 2a. So that's why it works. That's why you find it. So that's the intuition, is that the negative b over 2a is the direct middle between the two zeros, because all you're doing is you're adding and subtracting square root of b squared minus 4ac over 2a. So you could memorize this, and that is fair, but you could gather more information. You could understand the quadratic formula a little better. That's why it's negative b over 2a, because it's right in between the two zeros from the quadratic formula. Any questions on that? Isn't that cool? Objectively cool. In the context of this thing. In the real world, not very cool. Like getting a monster kill in Dota 2. That's a cool thing, right? If we've ever played Dota 2, which I've never done before. I've never played Dota at all. But if I did, I know that getting a monster kill is probably a big deal. getting a triple kill. That's a pretty good thing to do in that game. Very satisfying. But either way, getting sidetracked. So instead of having to complete the square on this, we can bypass that. And in fact, cool tip. Since the A value is the same in vertex and standard form, you can complete the square without completing the square. That is what I wanted to mention at the very beginning. The A value is the same. What do you need to have for vertex form? You need A, H, and K. What I've just shown you is that you can find the H and find the K value. The H value is negative B over 2A. The K value is plugging that value into the function. And the A value is the same. So you have everything you need. I'll show that in just a moment. Since the A value is the same, you don't have to do this. That being said, this is a memorization thing. So that's why if we've already memorized it one way, there's no need to memorize it a second way, but you can bypass it if you really choose to. So
Complete this.
you can complete the square without completing the square. So what do I mean? So your A value, this is your A value, this is your B value. So H of the vertex is negative B over 2A. So that's going to be negative 6 over 2 times 3, which is negative 1. That's the H value of your vertex. That's the X coordinate. And the K value is equal to F of negative B over 2A, which is F of negative 1, which would be 3 times negative 1 squared, plus 6 times negative 1 plus 1, which is equal to 3 minus 6 is negative 3 plus 1 is negative 2, right? 3 minus 6, negative 3 plus 1. Yeah, negative 2. But you can use your calculator. So we found H, we found K, we already know A. So from here, we can just say that the vertex is negative 1 comma negative 2, and that means that the axis of symmetry is x equals negative 1.
That's cool.
Right? Isn't that cool?
That's kind of cool.
So it's way faster. So check it out. So way faster to do, but there is purpose to have both of them. Once again, this is not going to save your life in any situation, but it's good practice for algebraic manipulation and mathematical deduction, which is always a good thing to have in your life. Honestly, I can tell you, do I use this in my daily life? I mean, yes, I do because I'm a teacher, but do I use this at all when I'm at the supermarket or trying to buy something online? No. But the processes that I learned through doing mathematical deduction really helped me break things down in my daily life for problem solving. So there is a point to having both of them. But this is the cool thing that you can do now. We found the H, we found the K, and the A is the same. So vertex form, H is equal to negative 1, K is equal to negative 2, A is equal to 3. So immediately, f of x is equal to 3 times x minus negative 1 squared plus negative 2, or in particular, 3 times x plus 1 squared minus 2. And if you are bored this weekend, complete the square by the old way, and you get the exact same thing, guaranteed. So if you can memorize the vertex formula, completing the square is a thing of the past. The only reason, once again, why I typically avoid it is because it's another thing to memorize, and I try not to memorize things. But that being said, now that I think about it, I'm kind of changing my mind as I teach this, right? This instance right now, because if you can just like, you don't even need to memorize the vertex formula if you have the quadratic formula memorized. So vertex form is a times x minus h squared plus k. We found h and k by using the vertex formula, and a is the same. It's 3, so we're all done. Very fast, but it does require a calculator.
You know, with the graphing and all this, it kind of reminds me when you used to learn the cheat codes.
Oh yeah. Like, does anybody remember Game Genies? Does anybody remember Game Genie? I still remember plugging in my Nintendo, my original Nintendo games into that Game Genie thing, and buying that booklet or renting it from Blockbuster. Good times. Anyone remember Blockbuster? Good times. Any questions? Sorry, I think someone had a question over here. Or you had to buy the game magazines. Yes, Ben.
With the quadratic equation, if the first part of B and the 2A
Mhm.
the bottom are the intercepts, what's the stuff in the square root for them?
So the square, I wish I had saved it, but x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. You can split this up. So I actually saw this on a couple people's exam zeros, is that they thought the 2a was only over the b, the negative b, but it's not. It's over the whole thing. But by the properties of division, you can break this up as negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. So the negative b over 2a gives you the midpoint between the two zeros. The square root of b squared minus 4ac over 2a, that when it gets added and subtracted, that gives you the actual x-intercepts, the zeros. And there's actually this thing right here, the b squared minus 4ac is what we call the discriminant. And what it does actually is tells you how many real zeros you have. Surprisingly enough, in math 283, which is Calc 3, that actually does show up in a very, very roundabout way when you're talking about minimums and maximums of surfaces in 3 space. So very, very cool. It's not very useful to know that, but it is an interesting fact that it shows up again on accident. So, like when you're proving how to find, there's a formula in Calc 3 that says that the relative extrema can be determined by f sub, I think it's been a while. It's been a while. X squared minus f of xy times f of yx. It's something like this. It's weird. It's weird, but that ends up being useful, and the proof of why it works ends up hinging on the discriminant. That's the reason why. But anyways,
That's here.
oh no, it's great. It's beautiful. It's Calc 3 is one of my favorites. One day I'll teach it. Least favorite, Math 120. I don't like teaching Math 120. It's just not my cup of tea. I don't like doing real life applications of mathematics. That's not fun. That's not fun. Theoretical, way more fun. So 120 is liberal arts mathematics, and it's all about applications of math, and that's not fun. Who cares about how you can use it? Far more fun to do theoretical. Okay. So, any questions on the previous one? Sorry, we got a little bit sidetracked talking about Blockbuster and Game Genie and stuff. Okay. Without graphing, determine where the function has a relative maximum or minimum value, and then find that value. So, the relative max / min occurs at the vertex. We can use vertex formula. And you know what? I'm feeling generous today. On the exam, I'll provide the vertex formula. I'll provide the exam 2. I'll provide the vertex formula. I'll do it. So, is this going to have a relative maximum or a relative minimum? Don't say it out loud. Let everyone get a chance to think about it. But utilize your knowledge right now to figure out if it's a relative max or a min. Let everyone get a chance to think about it. I'll give you the first hint if you're still stuck. Your A value is -2, which is less than 0. So this parabola opens down. So implies a relative max. So we have a relative maximum and we know it occurs at the vertex. So we'll use the vertex formula to find that relative maximum. So H is equal to -b over 2a. So in this case, that would be -8 divided by 2 times -2, which is -8 over -4, which is +2. So then K is f of -b over 2a, which is f of 2. We'll slow down for a second. Now, we would normally take our break, but I want to finish this. We got this one and the next one, and then we'll move on. And we'll take our break, and then we'll start up 2.2. So I think we're working our way. We're getting back on track, which is awesome. So once again, H value comes from the vertex formula. It's -b over 2a. So in this case, that b is 8, a is -2, so it's -8 over 2 times -2, which again becomes +2. The K value of your vertex comes from plugging in that X value into the function. In this case, f of 2. So I'll plug that into the curve. So that would be -2 times 2 squared plus 8 times 2 plus 3, which is equal to, is that right? 8, so that'll be -8 plus, 11. So utilizing this information, we have a relative max value of 11 at x equals 2. We found the H, we found the K. And by the way, if you want to, on this, like, so bonus, vertex form is y equals a, which is -2 times x minus 2 squared plus 11. Boom. No need to complete the square. You have your a value, -2. You have your h, +2. You have your k, 11. You have everything you need for vertex formula. Because vertex form is a times x minus h squared plus k. You got it all. Super nifty. Yes.
On the K, where'd you get, the number 2 after that? How'd you get that?
It's the two from each. Because he's plugging in f of,
Is that okay?
f of -0.
Yes. Great job, Hector. So it's coming from the -b over 2a. Excellent. All right. My favorite question from this, from these notes is this. Wait, not this one. We'll skip this one, actually. In the interest of time. Well, yeah, we'll skip it and do this one. This one's far more fun.
It's fun.
Yes, funds and the functions. Find the vertex form of the quadratic equation with the following properties. Then graph the function. The vertex is 3, -2, and it passes through the point 1, 6. So we can plot those points right away. 3, -2. It's right there. And it passes to the point 1, 6. So with that information, is this parabola going to open upwards or downwards?
Upward.
Yeah, it has to. It can't, like, since this is the vertex, it can't just magically go up to that and then go down, because then that wouldn't be the vertex. So that's a cool thing that we now know, is that it opens downwards. Or upwards, excuse me, upwards. But we need to find the equation. Okay. Well, vertex form is y equals a times x minus h squared plus k. The vertex is 3, -2. So we know h is 3 and k is -2. We already know 2 of the unknowns, because x and y are your variables. They will vary with time, but a, h, and k are fixed numbers. But we just found, because we're given the vertex, we know what h and k are. So we have that f of x, or y, whatever you want to call it, f of x is equal to a times x minus 3 squared minus 2. What's a? How can I find it? Yes, Ben.
Plug in the 1 and 6.
For x and y.
Yeah.
Exactly right. We know a point on the curve. And remember, so what was Phil's theorem? If 1, 6 is on the graph, f of 1 is equal to 6. That's my theorem. That's my theorem. If a comma b is on the graph, then f of a is equal to b. So if 1, 6 is on the graph, that means that f of 1 is equal to 6. So we can plug in 1 for x, and then whatever that value is, that needs to equal 6. So f of 1 is equal to a times 1 minus 3 squared minus 2, and that has to equal 6. Anybody have any questions on that? Isn't that cool? That's clever. That's very, very nice. This problem was trying to remind us of a lot of different facts. Going back to Phil's theorem in 1.3. If 1, 6 is on the graph, then f of 1 has to equal 6. So that's going to be -2 squared, but that's 4, excuse me. So we have 4a minus 2 is equal to 6. That gives me 4a is equal to 8, which gives me a is equal to 2. So we have everything we need. We have h, we have k, we have a. We're all done. So y equals 2 times x minus 3 squared minus 2. That is our formula. And in fact, by the way, we didn't even need the formula to find another point on the graph. Why? I'll give you a hint. Because of the symmetry in the vertex. We have the axis of symmetry because we have the vertex. So since this point is 2 units away from the vertex, there's an opposite point equally distant right there at 5, 6. And so we have everything we need to graph it, and we're done. I like that problem a lot because it uses our knowledge of functions and everything to do it. They shouldn't say find the function. They should say find the fun. Okay, let's take our next break. Let's come back at 11:47 and we'll start up unit 2.2. All right. People watching the recording, get up and stretch and do some squats or some guided meditation. I don't care. Welcome back, or not welcome back. We're still here. So we're starting up the new unit. So we're going to talk about we focused on degree 2 polynomials, and now we're going to generalize that to degree 3, degree 4, degree 5, and that's because after degree 2, their properties become a lot more difficult to define, and so degree 3 polynomials, degree 4 polynomials, they don't have any like consistent thing that they all share. So a polynomial function now we already in unit 0.3 or 0.4, I can't remember off the top of my head, but in that one we talked about what a polynomial is, but now we're just going to add on the function part of it. So it's going to be the same definition, but instead of just being an expression, now it's an equation, it's a function. So it's f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x to the first power plus a sub 0. That's the general formula, because remember, we're trying to, like, as mathematicians, we like to try and write things as general as possible. But a polynomial function could have any number of terms. It could be a degree 3000 polynomial, or it could be a degree 0 polynomial. So how do you encompass all of them? You use an arbitrary number n, where n is a whole number. It could be 5, could be 2 billion. And then a sub n through a sub 0, they're all just real numbers. Normally, the way we usually get to see them, they're all integers. So they're like -5, 2, 3, or whatever. But it's not impossible to have weird numbers like pi or square root 2. As long as it's not part of the x, you're all good. The whole number n is called the degree. And the way we abbreviate it is we write deg of f is equal to n. So deg meaning degree. And we had talked about it a while ago, but it's still, and it's way more relevant now. The number a sub n is called the leading coefficient. And the corresponding term, a sub n, x sub n, is called the leading term. I'm going to give more space. I'm going to make an edit. Sorry, 1 second. Unit 2.2, more space for leading coefficient. Apologies. Just want to make them better. Nope, not this one. That's the other class. Okay. All right, back to it. So a sub n x to the n is the leading term, where the coefficient in front of it is the leading coefficient. So we've already kind of done this, but it's still a good practice to get back to it. Is this a polynomial? Yes, it is. And it does a thing that I do not like, and I try not to do it, but Alex every once in a while throws this in as a wrench in the plan. But once again, I think we had this conversation about it. No real mathematician will ever write things other than in ascending order or descending order. So this one is written all jumbled around, which I will never do on an exam, but just in case it does happen in another textbook. So this is a polynomial. Yes, there's a division by 3, but that's the same thing. This is just 1/3 x squared. So it's all just a bunch of powers of x being raised to different whole numbers and with real number coefficients. So this is a polynomial, and its degree is 4. The highest degree term that I see is the 3x to the 4th. And so the leading term is 3x to the 4th. With a leading coefficient of 3. The next one, y equals 5. Polynomial, not polynomial? I was deliberately trying to be tricky. It is a polynomial. It's just a very boring polynomial.
What's the degree?
What's the degree?
Right.
0. It's a degree 0 polynomial, and its leading term is 5. So these are the uninteresting cases, which makes them interesting, honestly. There's a fact in mathematics that there is no such thing as an uninteresting number. And I could like if you want to see the proof of it, I can definitely show you the proof at some point. But there's no such thing as a not interesting number, not interesting whole number. But anyways, so these are just the simplest polynomials, are just the constant polynomials. They are degree 0 because they don't have like you could rewrite this as 5 times x to the 0 if you really wanted to. That's the reason why. This next one, is it a polynomial? No, it's not. This is not a polynomial, and I'll give you 2 reasons why. These are 2 issues. In order for it to be a polynomial, it needs to have whole number exponents on the x's, and you can't be dividing by variables in a polynomial because dividing by variables causes issues, right? Dividing by x makes it so that function g of x is not defined at 0 because you'll get 19 over 0, which is undefined. And polynomials must be defined everywhere. So the degree and the leading term, that's not available. All right. So,
Right, nar.
nar,
Nar.
nah, or none, or whatever you want to write. Okay, so one of the biggest things we study in mathematics, it's a big field of study, is the roots, or what we call like, so new textbooks, they say zeros. I like the terminology of a root for 2 reasons. And that's the way a lot of older textbooks will say it. A root tells you something more. There's a reason why we said root and we didn't say any other word. We chose the word root because what do roots do for a tree? They make the foundation, right? A tree cannot survive without its roots. And a polynomial is constructed by its roots. That's why I like the terminology. The other reason is because if you have a 0 at 0, it sounds really weird. There's a 0 at 0. Whereas if you say there's a root at 0, it's much more clear. But given a polynomial f, the value x equals c is called a 0 / root of f if f of c equals 0. That's what it means. That would be a 0 or a root of a function. Now, this definition is primarily focused on polynomials, but the concept of zeros and roots can be extended to any function. Any value that where your function equals 0 is like a root or a 0 of your function. But we typically talk about it in terms of polynomials. Now, note, f of c equals 0. That means your y value is 0. This corresponds, the roots are the x-intercepts. Of the polynomial. What happens when so to find an x-intercept, you set the opposite variable equal to 0. You set y equal to 0. Saying y is equal to 0 is the same thing as saying f of x or f of c is equal to 0. That's why these are the x-intercepts. It's precisely when your y values are 0. So now we get to do some factoring and stuff. Determine the zeros of the polynomial p of x equals 3x to the 5th minus 19x to the 4th minus 14x cubed. Well, okay. Zeros happen when p of x equals 0. Hence the terminology. I understand their argument on why to use the terminology 0, but once again, I think root is so much more in like such a better definition because it makes sense, as we'll see in a little bit. We'll see it in a second. So zeros happen when p of x equals 0. So that means we're going to set 3x to the 5th minus 19x to the 4th minus 14x cubed equal to 0. And to factor anything, we factor out a GCF first. I know it's been a while since we've had to factor, but it's still important. So we factor out an x cubed because 3, 19, and 14 have no common factors. So it becomes 3x squared minus 19x minus 14 is equal to 0. All right, and then I've got to factor that. So two numbers that multiply to negative 42, because that's 3 times 14. 3 times negative 14, right? 30 plus 12, yeah, 42. And the same two numbers need to add to negative 19. What numbers would those be? Not 7 and 6. So those add to 13. 4 doesn't go into it, 5 doesn't go into it, 6, 7, 8 doesn't go into it, 9 doesn't go into it, 10 doesn't go into it, 11, 12, 13 now, 14, 14 and 3 though, that doesn't work. 21, then 2. Yes, 21 and 2. Negative 21 and 2. Because I want it to be negative 19. That's why it's negative 21 and not negative 2. And then I'm going to use the AC box method, but if you want to use the bottoms up method or any other method you've learned, that's fine too. So 3x squared, negative 14, negative 21x, and 2x. We get 3x, 2x, and negative 7. So this factors to x cubed times 3x plus 2 times x minus 7 equals 0. And so by the zero product rule, the whole reason why we're doing this is we're trying to write it as a product of things because of the zero product rule. And the zero product rule says that if you have several things equal to 0, then each one can equal 0. So x cubed equals 0, 3x plus 2 equals 0, or x minus 7 equals 0, which gives us the roots or the zeros. X equals 0, negative 2/3, and positive 7. That's a terrible 7. Absolutely terrible. It's even worse now. All right. Any questions on that? Okay. So remember, and so that's this is a perfect example of why I don't like the terminology 0 and I like root, because otherwise we're saying there's a 0 at 0, negative 2/3 and 7. That just sounds circular. It sounds weird. Whereas if I say there's a root at 0, negative 2/3 and 7, it makes a lot more sense. It hits the ear better. Any questions? Okay. Then it says find the intercepts of the function 3 times x plus 2 squared times x minus 3 times x minus 1 to the 4th. So intercepts, I think I meant to say, well, so x intercepts, those are the zeros slash roots. So we're going to set f of x equal to 0. That's 3 times x plus 2 squared times x minus 3 times x minus 1 to the 4th equals 0. All right. And I'm writing this down wrong. So don't write this down. John Doe looks at that and says, I got this. That's x equals 0, negative 2, 3, and 1. Why is John Doe wrong? I mark off 1 point. Which one's wrong? Which 0 is wrong? Oh, don't break my heart, guys.
0.
We know the 0 because it's not 3x. If there's an x there, then you can set 3x equal to 0. But otherwise, you're trying to say 3 equals 0, which is ridiculous. So That's the reason why John Doe gets marked down and a bop on the nose saying bad student. So either 3 equals 0, which is ridiculous, colon, x plus 2 equals 0, x minus 3 equals 0, or x minus 1 is equal to 0. And that gives me x equals -2, 3, and 1. And I can write them as coordinate points if I want to, if the problem asked it. It didn't ask for them in a specific format. So as such, I can skip writing them as coordinate points. But if it said find the intercepts, write them as coordinate points, then I have to write them as -2, 0, 3, 0, and 1, 0. That's that. And then the y-intercept, as a reminder, the y-intercept comes from finding f of 0. Because a y-intercept, you set x equal to 0. That's the same thing as substituting 0 into the function. That becomes 3 times 0 plus 2 squared times 0 minus 3 times 0 minus 1 to the 4th, which ends up being 3 times 4 is 12 times -3 is -36 times -1 to the 4th. So it's -36, right? Let's check. Let's use our calculator. Who can beat me? Anybody do it faster? Yep, -36. All right. So that's how we find the zeros. We set the function equal to 0. If we have to, we can factor it. Now, right now in our mathematical career, we can only factor quadratics. So at best, right now, and then there's a few situations with cubics, if you remember factoring by grouping. If you have a quadnomial, you can factor by grouping. So right now, that is the only things we can do. So as you'll see up above, this one actually factored and then gave you a quadratic. Later on, when we get to 2.4, 2.4, we will learn another way to factor it without factor any size polynomial, but it's not foolproof, but we'll get to it. So,
We go back.
oh, go ahead. Yeah. Thank you for letting me know. All right.
Question,
Yes, Ben, what's up?
Why would we not also solve for x on the first one for the x-intercept? I understand why we're doing like the part, but if we want all of them, should we like condense and simplify what we have so far and then solve for x from there?
So it's this one right here, it's already broken up into the product of pieces. So if we were to FOIL it out, which one thing for certain, that would be a lot of work because we'd have to FOIL out a square, FOIL out a fourth power, unless you want to bust out Pascal's triangle. I don't want to do that. And then I'd have to degree 4, so x minus 1 to the 4th power, that would be 5 terms. And so then I have to FOIL in an x minus 3, and then I had to FOIL in a trinomial. It would be a lot of work. And unfortunately, it would just give me the polynomial unfactored. And then I wouldn't be able to find the zeros at all. It is important to know how like what the standard form is, like the expanded form. That does play a role, which we'll see soon, but it's not going to give us the zeros. So some graphical properties, and this is something they want us to talk about. Polynomials are continuous, and another calculus concept that we don't even really talk about in regular calculus. That only came up in my conversations. Smoothness only came up when I was talking about math, like a 400 level math course. We usually just say it's differentiable, but either way. These are calculus concepts, but for now, the intuition will be enough. Continuity means a continuous line and there's no breaks in the graph. So the first one is continuous. The one on the bottom left, that is continuous. This is not continuous.
Like that one chowder,
That what?
the one chowder,
Shouter character?
chowder character.
I don't.
Cartoon.
Oh, sorry, I don't know. Unfortunate. I'm sorry. I try to stay up and up on relative media.
From the early 2000s.
That was only a couple years ago, right? 2000 was only a couple years ago. I've forgotten concepts of time after COVID. But anyways, so this one, it might be something other than a polynomial, but it probably is a polynomial. And this one, because there's these breaks in the graph, I can't draw it with one continuous line. That's why it's not continuous. Now, smoothness is that it's a smooth graph, smooth edges. And there's no corners or sharp edges. So it's exactly what you'd think. It's a piece of spaghetti instead of being like a piece of uncooked spaghetti. Well, no, uncooked spaghetti is just straight line, but you get the idea. If you were to cook a piece of spaghetti and just throw it on the ground, it would be all smooth-like. It wouldn't have any jagged edges, otherwise it would break apart. So this is smooth, the first one, and this is not smooth because of that point right there. And so the point being is if you're looking at graphs of like if you're given a bunch of graphs, you can determine which ones are polynomials based on that requirement. They have to be smooth and they have to be continuous. So if it asked you, if there's a question on the exam or on your homework and saying which of these graphs are could possibly be polynomials, this could be a polynomial, this could be a polynomial, but this can't, and neither can this. That's what that's trying to do. Oh, as we see right here. First one, top left, polynomial, not polynomial.
Yes.
Yes, polynomial. This is a polynomial. Second one, top right. Nope, not a polynomial. Bottom left. Nope, it's not continuous. It's smooth for the most part, except for a -1, but it's not a polynomial. And the last one, it could be a polynomial. I think that one will actually be, well, no, it's going to be a polynomial unless it continues to go like that, in which case it's going to be a trigonometric function. But I don't know what polynomial. All right. So that's how we can distinguish between them. They need to be smooth. They need to be continuous. All right. So one of the things that there are two big things we're going to study in this section. One of them is end behavior, and one of them are zeros. Because knowing end behavior and knowing the zeros, you can graph any function you want, any polynomial you want. But in order to do that, we need to have some notation, some jargon. So if you see this terminology, x arrow positive infinity, what that's saying is that x is becoming infinitely large in the positive / right direction. Because as your x values are getting larger and larger, you're moving further and further right on the number line. And that's in the positive direction. Whereas if it says x arrow negative infinity, the way we read that is we say x is approaching negative infinity. Because remember, infinity is a concept. It's not a number. So when we say x is approaching negative infinity, we're saying that our x values are becoming infinitely large. They're becoming very, 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 very large. But if we're approaching negative infinity, our x values are becoming infinitely large in the negative / left direction. Then you can also talk about it in terms of your function. And remember, f of x is synonymous with y. So if you're saying f of x is approaching infinity, that means that your f of x value, your y values, so I'm going to put this underneath it, aka y, your y values become infinitely large in the positive direction. But that's going to be the up direction. Because if your function values, which are your y values, are getting positive, more and more positive, that's going up on the y-axis. And then if you're having f of x approach negative infinity, that's going to infinitely large values in the negative / down direction. Now, that is the way calculus wants you to write it. That's the way calculus wants you to write it. However, a lot of the times, and our textbook is no different, they finally decide, for whatever reason, they want to keep in continuity, but they don't want to include this. And so they'll use an alternative notation. I will accept any of the following notations to denote end behavior. So, and furthermore, what is end behavior? End behavior is what's happening at the ends, right? It's what's happening all around here, around the border. Not what's happening locally in the middle. It's saying what's happening as we move further and further out on the graph. And so for this picture of this generic polynomial, as x goes to positive infinity, I'm going to highlight this one and let's use blue. No, let's use purple. So as our x values go to positive infinity, so that's x going to positive infinity, we see that our y values keep going down and down and down and down. So we see that f of x is approaching negative infinity. As our x values get infinitely large, our y values, like infinitely positively large, our y values get infinitely negatively large. So f of x is approaching negative infinity. The other way, and this is the way that our textbook says it, is that it falls left. It falls on the left. It falls off the ground. And that makes sense. And so if you say it in calculus notation, I'll give you full credit. If you say it in this notation, which is the way our book says it, I'll give you full credit. Another way that students will write it is they'll write this. And that's fine too. I know, so in most McGraw-Hill textbooks, which is what we have because it's Alex products, they use the falls and rises, but there's a couple books by Pearson that use this notation. So if you're looking at a textbook and they say that, that's fine too. I'm going to be partial to this one or the first one. Those are my favorites. And so, and then, oh yes, Hector.
Where does it say fall left, fall right?
Oh my God. I promise you I know my right from my left. I promise. It falls on the right. Falls right. I'm so sorry. Oh my God. I swear I know my lefts from my rights. I swear it. Okay, so it falls on the right. Thank you for catching that. Thank you. I'm assuming everyone was confused by that fact. Yes, it falls on the right. On the right side of the graph. Then let's use pink, or no, let's use orange for this one. As x goes to negative infinity. So if we're approaching here, x is going to negative infinity. Then you see that your function values, your y values, keep going up and up and up. They get indefinitely large in the positive direction. So we see that f of x approaches positive infinity. And the alternate notation is that it rises left. Or you could write it like this. Both are acceptable. All three are acceptable. I will give credit for any of them. but I know Alex wants it to be rising and falling left or right. So that should do it for now. And then we'll talk about the leading term test when we get back and why we want to study end behavior and those things. But that'll be on Tuesday of next week, because on Thursday of this week, we have our exam on Unit 1. It's 1.1 to 1.7. There's an exam review that you can use to help you study. It's an hour and 20, just like usual. As soon as you finish it, you're free to leave. And yeah, if you have any questions, please feel free to email me or come to my office hours. Otherwise, have a great rest of your day. Happy studying, and I'll see you on Thursday for the exam.